Which one?
Good morning. We'll start constructing some classes of generalized diffusion processes. But first, I would like to write down some formula that are called perturbations formula. So, suppose that we are given by operator valued function b as x and vector value a as x as x from 0 t cross rd. And suppose that the conditions on these functions are fulfilled that provide the existence of a fundamental solution to the corresponding parabolic equation. Okay, and so G S X T Y is such
Recording in progress.
a fundamental solution that solves the following Cauchy problem. U prime S plus A S X U prime X plus 1/2 trace B S X U second prime X X equals minus F S X or S X from 0 to T cross RD. T is some point from this interval, okay? And U T minus X equals phi of X, or X from RD. Here, f and phi are given functions, and we know how to write down a solution to this equation under some assumptions about the function phi and f. It can be written as follows: U S X equals integral over RD G S X T Y phi of Y dy plus integral over G S X tau Z F tau G dz. For example, phi, if phi is a bounded and continuous function, and f is a bounded and continuous, and it is local, it satisfies locally Helder condition. It is Helder locally, Helder continuous in space argument uniformly with respect to tau. So this solution is a classical solution. It is twice continuously differentiable in x, and continuously differentiable with respect to s, and is the solution to this problem. But we can consider this problem from another point of view. Let us denote by G0 S X T Y the fundamental solution to the following problem. U prime, maybe U prime S plus 1/2 trace B S X U second prime X X equals 0. Okay, or maybe some function minus f s x, and G0 is a fundamental solution to this equation, this short equation as compared with this one. Okay, and you see, if I can write down a solution to this equation as follows: integral from s to t d tau integral G0 s x tau z f tau z dz. Okay, but according to this formula, this is a solution to this equation that satisfies 0 final condition. Okay, under some assumptions with respect to f capital. Okay, and now let us write down this equation with let us put here f being equal 0 identically. Okay? And write down this equation in the following form. U prime s plus 1/2 trace b s x u second prime x x equals minus a s x u prime x. This equation is, if this is f capital Sx, I can write down a solution to this equation with the help of this fundamental solution, G0. Okay? And the solution of this equation which satisfies 0 final condition can be written as follows: U S x equals integral from s to t d tau integral or rd g0 sx tau z multiplied by a tau z u prime z dz. Okay? So we use this fundamental solution for this short operator, okay? In order to write down some integral equation with respect to u, integral differential equation. And if we are going to construct a solution with non-zero final condition, so we should add the following integral g0 sx tau z phi of z dz. So you see, I expect to solve this problem that corresponds to two given functions, b and a. I expect to solve this problem knowing only the fundamental solution to short equation. And instead of this second order differential equation, I obtain some integral differential equation with respect to this function usx. Okay? And I am sorry, here must be written t, not tau, t. Okay. So we arrive at the following equation. I know that this function usx okay. So if I put here phi is delta function, Dirac's delta function, concentrated at the point y, so this must be G fundamental solution to the long equation gsx ty equals, here we have g0 sx ty and here we have derivative. So we have integral from s to t, the tau integral over rd, g0 s x tau z, a tau z, g prime z tau z t y dz. So you see, this is the fundamental solution to the long equation, and G0 is the fundamental solution to this short equation. Okay? So they must be connected with this relation. Okay. And I can use the same reason for if, so I know that G is fundamental solution that corresponds to AB. Okay? G0 is corresponding to G, to B. Okay? So I can, so we add, if we would like to add to this diffusion operator some drift, we have to write down this equation for G. G is expressed through G0. But this is an integral differential equation with respect to G. Okay? And now if I apply the same reason to this, G, and I would like to add to it the drift vector minus A. So I should write something like this, but instead A, I should write down minus A. So, and I know that as a result, I receive the G0, okay? So G0 must be equal to starting process G S X T Y minus integral the tau integral G S X tau Z A tau Z G G0 G prime 0 Z tau Z T Y Z. And this equation can be written in the following way: GSX TY equals G0 SX TY plus this integral the tau integral over RD G SX tau Z A tau Z G0 prime Z tau Z TY dZ. So this is a pair of equations I delete this one. So we have this pair of equations. If we know G0, then G can be found out as a solution to each one of these equations. You see, this equation with respect to G is an equation for this function as a function of the first pair of arguments. So this is an analogy to Kolmogorov's backward equation. And the second one, you see, G is an unknown function, and the first two are parameters here, fixed parameters. And this equation is an analogy to Kolmogorov's forward equation. If the function a as x satisfies the conditions under which the fundamental solution exists to the long equation. So a is a continuous bounded function that is Hilbert continuous with respect to this argument, with respect to space argument. Okay, so we know that this fundamental solution exists and this one exists, and they are connected with the help of these equations. Okay, but now we may try to solve this equation, not necessary for such a nice function, not nice functions as in that theorem I mentioned. Okay, and I am going to show how to solve this equation in the following situation. Let B as x be such as in the theorem on the existence of fundamental solution G0. Okay, it's a nice function. I would like to recall B as x is a bounded function. It is uniformly non-degenerated, and it is Hilbert continuous in both arguments, s and x. Okay? So there exists the fundamental solution G0 for short equation. And now let us assume that a function ASX is given for SX cross RD. It is RD valued function. And suppose that the following integral ASX, this is a vector, this is norm vector norm, to the power P tau dx is finite. Okay, and we denote this integral by norm AP. So we have a nice diffusion operator and not very nice drift vector. This function can be locally unbounded. Okay, and I am going to show that there exists function gsxty, a solution to each one of these equations. Okay, and it is similar to diffusion. We will see that some properties of this function is like that of a diffusion, like that in the case if A is also nice function. Okay. And now how to solve the one, for example, the first one of this equation. We can integrate if phi, a real valued function, smooth enough, is given. We can integrate this equation with this function gsx ty dy, denoted by, I forgot, maybe u or maybe u s x t phi. Okay, and we will receive for that function the following equation: u s x t phi equals integral g0 s x t y phi of y dy plus integral integral G0 S X tau Z A tau Z U prime Z tau Z T phi Z. Okay, G0 is fundamental solution to the short equation, and we know its properties. As a rule, such equations are solved by the method of successive approximations. We put U0 S X T phi being equal integral G0 S X T y phi of y dy, and for k greater than 1 uk S X T phi equals integral d tau integral rd G0 S X tau Z A tau Z U prime K minus 1 Z tau Z T Z. So U prime K minus 1 with respect to Z prime with respect to Z, okay? Okay. And now we should obtain some estimates through norm, P norm of this function. Okay? Or maybe it would be better. No, okay. It would be better one. So the first function, the zero function, is estimated by norm phi, okay? But we should substitute here the derivative with respect to x of that function. So du0 dx sx t phi. Maybe let us denote it by nabla x u0. this is a vector. This is the same as u0 x, u0 prime x. The same, okay? The vector. So the estimation is as follows. Norm phi integral over rd nabla x g0 s x t y, absolute value or norm of this vector dy, and we know estimates. That's estimations for function g0. I would like to recall we have the following inequalities: dx L ds m g0 s x t y is less than some constant. It depends on t. We consider our consideration concerns this space. It depends on t, and t minus s to the power minus d plus L plus 2m over 2 x minus mu y minus x squared over t minus s, where L and m are non-negative integers such that 2m plus L is not greater than 2. So if m equals 0, L may be equal to 0, 1, 2. If m equals 1, so L is equal to 0. Okay, and we have here exactly the case when m equals 0 and L equals 1. So we have here minus d plus 1 over 2. So we can continue that estimating, and write down here k norm phi t minus s to the power minus m plus 1 d plus 1 over 2 integral exponent minus mu y minus x squared over t minus s dy. And as a result, we have here constant normal phi, maybe the other constant, t minus s to the power minus 1/2. Okay, so the function u1 s x t phi. Let us estimate the function u1, the absolute value of that function. Okay, so I apply to these integrals the Helder inequality. So the integral of this function gives the norm of this function gives me norm A P. Okay, and here I will have constant norm phi integral d tau over tau minus s t minus tau to the power 1/2 multiplied by p over p minus 1 multiplied. Okay, and integral over rd g0 s x tau z to the power p over p minus 1 dz and to the power p minus 1 over p. And we should determine that p for which that p, I do not know which one, which numbers I can choose for p. Okay, but I have some condition. This integral must be convergent, must be well defined. Okay, so I should calculate how to choose p in such a way that this estimation is this integral is finite. Okay, let us make a little break. Let us continue our considerations. So we have to estimate this.
Recording in progress.
So this integral g0 s x tau z to the power pi over pi minus 1 dz we have estimation for g0 some constant we have here tilde here k tau minus s to the power minus d over 2 p minus 1 and integral exponent minus mu p over p minus 1 y minus x square z minus x over tau minus s dz. Okay, this integral is calculated, but I write down it as the new constant k1 tau minus s to the power minus d over 2p minus p minus 1 okay, plus d over 2. Equals k1 tau minus s to the power p minus 1 plus minus d over 2 p minus 1. Is it true? Minus 1 plus. Okay. So you see, we have we have substitute here this estimation and we obtain the following integral. The following integral from s to t d tau integral from rd over rd. Oh no, sorry. Integral t minus tau to the power p over 2 pi minus 1, and here tau minus s to the power minus d over 2 p minus 1 d tau. And you see, this is a positive number, yes? And this is negative, and it...
So should it be minus or the first one?
Oh, yes, yes. Thank you. Thank you. So, this number should be less than 1, and this one, d over 2 p minus 1, is less than 1. From the first one, we have 2 pi. Pi is greater than 2. Okay? 2 pi minus 1. P is greater than 1. Okay, in the Helder inequality. Okay, and here P must be greater than d over 2 plus 1. Okay, but this is the estimation. So if P is greater than 2, then we have some nice estimation for U1, but we need not U1, but the derivative of U1. So let us calculate the nabla U1 over x, nabla x of U1 norm. We have here integral over RD nabla x g0 s x tau z norm. And here estimation was, I forgot it. We have estimation for U prime, some constant, maybe it will be included in that one, and t norm phi and t minus tau to the power minus 1/2. Okay, but we should write down here p to the power p over p minus 1, and here p minus 1 dz, and here p minus 1 over p. Let us find out when this integral is finite. So here we have tau minus s to the power minus the derivative minus d plus 1 over 2 to the power p over p minus 1. Okay, and this function t minus tau to the power minus p over 2p minus 1, this one, okay, and exponent give us some constant and tau minus s to the power d over 2 without p. Okay, and I should integrate this expression with respect to tau on the interval st. Okay, so this singularity at the point t is integrable if p is greater than 2. Okay, so I should consider this one. We have here d, the exponent d over 2 minus d plus 1 over 2 p minus 1. So p minus 1 minus 1 half minus 1 half plus 1 minus d plus 1 over 2 pi minus p minus 1. Is it good? Okay. So the number d plus 1 over 2 p minus 1 plus 1 half should be less than 1.
Greater than negative 1.
This greater than negative 1.
Oh, okay. So this is with minus.
Yes. Okay, and what? So we have some estimation for p. P minus 1 is greater minus 1 plus d plus 1 plus minus 1 d over 2, d plus 1 over 2 plus p minus 1 over 2 oh no,
So if you subtract 1/2 and multiply by 2 and then by p minus 1, you will get p minus 1 greater than d plus 1. So p
d plus 1.
so
It's-
probably p greater than d plus 2.
I agree.
P greater than d plus 2. Yes, this is true. But
Move 1/2 to the right hand side
okay,
and multiply
and
by 2.
d plus 1 over p minus 1 is less than 1/2.
No, less than 1.
Less than 1. Okay, p is greater than d plus 2. Oh, this is true. P is greater than d plus 2. So, if a is such a function that for some p greater than d plus 2, we have a nice estimation here. And we can apply induction here and receive some nice estimation. I am not going to consider this. We have some estimation that the such that u k maybe nabla z u k tau z t phi some ck t minus tau to the power minus d plus 1. Oh no. d u p oh. Minus 1/2 plus k gamma. Okay, normal phi and some constants ck such that the series is convergent. So, and gamma is the following number: p minus d minus 2 over 2p. This is positive number, a positive number. Okay, so estimation is very nice. If k equals 0, we have the estimation for u0, nabla u0, and then it will be better, because we have here k gamma. So the series of the derivatives is convergent. So the function u is well defined. It is also the sum of UK SX T and the following properties of USXTV, the following properties can be established for that function. First, USXTV can be represented in the following way. Integral over RD phi of y g. Maybe let us write down G capital G S X T Y dy, where G S X T Y is a continuous solution to each one of those equations that were written for this function. I recall them: G0 S X T Y plus integral G0 S X tau Z nabla Z G tau Z T Y A tau Z T Z. The second one, this is the backward equation, and the forward is written as follows: G0 S T Y plus integral G S X tau Z nabla Z G0 tau Z T Y A tau Z dz.
Why do we have the same capital G for both equations? We solved only backward.
I explain. I will explain how to prove this. We can apply the method of successive approximations to this equation, but we should formally differentiate it with respect to x in order to obtain some integral equation. So if I denote by V S X T Y the nabla X G S X Ty. Then I will have the following equality for V equation. Vsx Ty equals nabla G0 Sx Ty plus integral nabla G0 Sx tau z V tau z Ty A tau z dz. Okay, and we can apply the method of successive approximations for this equation, and V0 is this one, V0, and Vk Sx Ty equals integral over Rd nabla x G0 Sx tau z V k minus 1 tau z Ty A tau z dz. Okay, and using some estimations like those we have made just now, okay, we can construct the function v as the sum of Vk, okay, and if I substitute this way into this equation, I obtain the function Gsx Ty, and this equation in the estimation for the sum Sx y is some constant, is the estimation is this is the worst term. The next estimation would be better. Okay, so k t minus s to the power minus d plus 1 over 2 exp minus mu y minus x squared over t minus s. So we can substitute this function here, and this integral is well defined. And what we know about that function g? The first equation is evident, because if I multiply both sides of this equality by phi of y, I receive that equation. We consider it. We have considered it, okay? And the second a second. If the function a as x satisfies the conditions of the theorem on the existence of fundamentals solution, okay? Satisfy the conditions of the theorem on existence of fundamental solution to corresponding to pair AB. Then G S X T Y exactly is that fundamental solution. That constructed, that the function constructed in this way coincides with that fundamental solution. Then G S X T Y coincides with the fundamental solution. Okay? And therefore it satisfies both equations. Okay? In this case. And the following property. If I have a sequence of the function an such that norm that a converge in the norm of this norm as n goes to infinity. Then the corresponding Gn S X T Y goes converges as n goes to infinity to G S X T Y in the following sense. We can obtain the following estimation. G N S X T Y minus G S X T Y is less than some constant that may be denoted by some other letter, n t minus s to the power minus d over 2 norm a n minus a t and exponent y minus x squared over t minus s. So you see, if plus t minus s is greater than delta, so the convergence is uniform with respect to all the arguments for fixed delta. So this, and for Gn we have, because norm an supremum over n is finite, so for Gn we have standard estimation GNSX T y, some constant T minus S to the power minus D over 2 e to the power mu y minus x square over T minus S. M does not depend on n, so we can pass to the limit in both those equations for the function g. And this made us able to assert that the function g is non-negative integral over Rd g s x t y dy is equal to 1, and g satisfies the Kolmogorov-Chapman equation. G s x t y is equal integral g s x tau z g tau z t y dz. So this is the transition probability density of a Markov process. The estimation shows that the corresponding process can be chosen being continuous, okay, because the standard estimation for G is true, okay, and the following equalities are true: y minus x theta, g s x t y dy equals integral d tau integral or Rd a tau z theta g s x tau z dz. And integral over rd, this is 1, and this is the second one. Y minus x theta square g s x t y dy equals integral d tau integral rd b tau z theta multiplied by g s x tau z and plus 2 integral d tau integral a tau z theta multiplied by y minus z minus x z minus x g s x tau z dz. These equalities show that our process is like diffusion one, okay? But the function a is maybe locally unbounded. It must be from LP for some p greater than d plus 2. Okay?
So our estimates allow us to pass to a limit from
Yes.
smooth to this.
Yes. For smooth function a to a general one with this property. Okay, that's all for today. Thank you. See you next Tuesday.